The paper discusses the dynamic maximum covering location problem, a variant of the MCLP that considers the installation of facilities across multiple time periods. It proposes an accelerated Bender's decomposition and local branching scheme to tackle large-scale instances of this problem. The authors expand upon the current state-of-the-art branch and Bender's cut solution method for the static case, introducing several acceleration techniques and a novel distance metric for the local branching scheme. This approach aims to efficiently and exactly solve subproblems. Computational experiments comparing these methods are also presented. The maximum coverage location problem, or MCLP, is a widely applied optimization problem that has been utilized in various fields, including emergency services, healthcare, and disaster relief. The dynamic MCLP, a variant of the MCLP, considers facility planning over a long time horizon, divided into discrete time periods. This formulation is crucial in situations where demand varies across time, infrastructure planning persists across future periods, or real-time operations require exact positioning. In the dynamic MCLP, open facilities can remain open, change location with or without cost, or relocate each time period. Despite its importance, no exact method exists for solving large-scale dynamic MCLPs. The only exact method employed in the literature is branch and bound, which has successfully solved instances with limited sizes. Heuristic methods, such as simulated annealing and greedy methods, have also been used, but with limited scalability. In contrast, specialized methods for the static MCLP have been able to solve larger instances. The need for a specialized method for the dynamic MCLP is evident, particularly in cases with significantly more users than facilities, which can occur when using fine discretization of continuous demand or creating multiple scenarios to model uncertainty. This work extends the branch and Bender's cut approach for the static MCLP to the dynamic case, introducing a suite of acceleration techniques to improve computational efficiency. By tackling the dynamic MCLP, this research aims to provide a more effective solution for large-scale problems, particularly those with significantly more users than facilities. The authors present a comprehensive framework for solving the dynamic multicover location problem, tailored to address the complexities of real-world applications. The framework consists of 4 key components: a range of tailored methods for the dynamic MCLP, a specialized local branching method, a novel subproblem solution method, and extensive computational results. The tailored methods include an intuitive multicut generation technique, an efficient Pareto-optimal cut generation technique with a closed-form solution, a partial Bender's decomposition strategy, and a Bender's dual decomposition approach. These methods leverage the problem structure to efficiently generate high-quality cuts. The specialized local branching method is embedded within the branch and Bender's cut framework and utilizes a new distance metric for defining subproblems based on the problem structure. The novel subproblem solution method can efficiently solve the local branching subproblems in an exact and proven-valid manner. Computational results are presented, comparing the proposed methods to existing approaches using real data from an electric vehicle charging station placement case study. The results demonstrate the effectiveness of the author's methodological contributions in providing high-quality solutions to large-scale instances, outperforming the greedy heuristic in Lamontagne et al. 2023, and providing performance guarantees via optimality gaps. The maximum covering location problem, MCLP, is a classic problem in operations research and location science, aiming to locate facilities to maximize user coverage within a limited budget. Exact methods, such as branch and bound techniques, are employed to solve the MCLP. For instance, Carvalho and Ribal, 1996, developed a branch and bound algorithm to ensure optimality. Pereira et al. 2007, reformulated the MCLP as a p-median problem and used a column generation procedure, incorporating stabilization techniques and limits on columns generated in total iterations. Carvalho et al. 2019, projected out variables associated with user coverage in the Bender's subproblem, providing an analytic solution for the Bender's dual subproblem, facilitating the solution of large-scale problems through a branch and Bender's cut framework. Heuristic methods, including greedy methods and simulated annealing, are also discussed. The greedy method constructs a solution by repeatedly opening a facility, selecting the one causing the largest increase in coverage. Simulated annealing, used in Murray and Church, 1996, simulates metal cooling, controlling the mutability of the current solution. A comparison of these heuristics was conducted in Shaw et al., 2009, where simulated annealing found the best quality solutions, although the greedy method solved instances faster with solutions within a 1% relative gap of those of simulated annealing. The authors also present a general formulation for the dynamic MCLP, which contributes to the literature on exact methods for dynamic MCLPs. This includes a binary decision vector X for facility existence and an auxiliary decision vector Z for user coverage, aiming to maximize coverage within a budget. The table showcases a variety of methods proposed for solving the dynamic maximum covering location problem, MCLP, including both exact and heuristic approaches. The MCLP is formulated to maximize the demand covered over all time periods, subject to constraints ensuring the feasibility of the solution. The objective function aims to maximize the total demand covered, with constraints defining the feasible domain, restricting the number of facilities, and imposing diversification or precedence constraints. This includes strategies such as greedy, simulated annealing, branch and bound, and grasp for tackling the complex problem. The variables X and Z in the dynamic multiple covering location problem, MCLP, must be binary, with integrality on ZTJ relaxable in constraints, 1e. For a given solution X in omega, the resulting coverage or total demand covered by the set of facilities defined via X can be calculated as f x equals n array summation T equals 1 Tx n array summation J element of J min 1 n array summation I element of I at dj xti dtj. The paper presents an accelerated branch and Bender's cut approach tailored for the dynamic MCLP, generalizing the current state-of-the-art approach in the static MCLP. This involves developing a single-cut Bender's decomposition method, where the Z variables are projected out of model 1 and replaced with an auxiliary variable theta. The main problem, MP, in iteration V is formulated as maximizing theta, subject to constraints, 1b and 1d, and op pi r, sigma r, x, is greater than or equal to theta. The Bender's subproblem is feasible for all x in omega, so feasibility cuts are not necessary. The candidate solution in iteration V is denoted as x, which is assumed to be integer feasible unless otherwise specified. This sets the stage for the development of acceleration techniques to strengthen the formulation and accelerate convergence in the dynamic MCLP. The Bender's primal subproblem, BPS, is a maximization problem with constraints, where the objective function aims to maximize the sum of coverage variables ZTJ across all time periods and users. Constraints include upper bounds on ZTJ based on the coverage provided by the solution X, as well as non-negativity constraints for ZTJ. The Bender's dual subproblem, BDS, is a minimization problem that finds the optimal dual variables pi tj and sigma tj, which are associated with the constraints of the BPS. These dual variables are determined by the coverage level it, with different solutions for when it is less than, greater than, or equal to 1. The resulting optimality cut, derived from the dual subproblem, is a function of the variables x and takes the form of a constraint in the master problem. This constraint ensures that the sum of coverage variables over all time periods and users must be at least theta. The Bender's decomposition algorithm iteratively solves the primal and dual subproblems to generate optimality cuts that are added to the master problem, gradually tightening the relaxation until an optimal solution is found. This section of the paper delves into the optimality cuts for the dynamic MCLP, drawing on the work of Curdo et al., 2019. 3 types of optimality cuts are defined: B0, B1, and B2, each based on different expressions. The cuts, BO, are dominated by B1, and the condition for J element of J's ensures that it is less than or equal to 1 will always be satisfied. These optimality cuts are valid for both integer and fractional candidate solutions. An example is provided in Figure 1, illustrating the cuts for a candidate solution x equals 1, 0, 0. The cuts correctly identify the objective value of solution x as 20, matching the value in equation 2. However, when used to calculate the objective value of another solution x equals 0, 0.75, 0.75, the results differ from equation 2. This discrepancy sets the stage for exploring improvements in convergence rate in the next section. The paper discusses the application of known techniques to improve the dynamic multi-commodity location problem, MCLP, decomposition method, focusing on strengthening Bender's optimality cuts and enhancing the dual bound. It begins with a simple example featuring 3 facilities and user coverage, as depicted in Figure 1. Primal heuristics are employed to provide warm start solutions, which can be challenging during early iterations of the Bender's decomposition method. This approach helps obtain a good lower bound on the optimal objective value. Additionally, valid cuts are added to the main problem to tighten its linear programming, LP, relaxation, as seen in Santoso et al. 2005, Codato and Fischetti, 2006, and Costa et al. 2012. The paper also explores modifying the Bender's subproblems, such as changing the set of users J, altering the frequency or type of cuts, or directly reformulating the Bender's primal subproblem, BPS, or the Bender's subproblem, 4. These improvements aim to enhance the efficiency and effectiveness of the dynamic MCLP decomposition method, making it more suitable for solving complex optimization problems in logistics and supply chain management. The Bender's decomposition algorithm is a crucial tool for solving the dynamic user equilibrium problem in public transportation systems. Enhancements to this algorithm include pre-processing techniques that aggregate users based on their coverage from facilities, reducing the size of J and the number of IT to be calculated in each iteration. Techniques such as those proposed by Ligo and Freisinger, 2022, which aggregate users with identical facility coverage, or heuristic methods like those found in Depakova et al. 2003, and Krag et al. 2014, are effective but have a negligible effect on user marginal effects and cut generation time, making them less critical. Generating cuts at fractional solutions is another key aspect of the Bender's decomposition algorithm. Curdo et al. 2019 demonstrated that generating cuts at every node in the search tree, regardless of whether the corresponding solution is fractional or integer, can lead to increased solving time due to the computational effort required for generating cuts with minimal benefits. Botten et al. 2013 suggested generating cuts at fractional solutions only at the root node, which provides a more balanced approach between computational efficiency and solution accuracy. The multicut method is also explored, allowing for more optimality cuts to be generated each iteration of the Bender's decomposition, accelerating convergence as noted by Burge and Luvo, 1988, and Contreras et al., 2011. This method involves replacing the auxiliary variable theta by the sum of new variables theta tfor1 is less than or equal to t is less than or equal to t, and then formulating a new MP with constraints and variables adapted accordingly. The BPS and BDS, along with the process for deriving the Bender's cuts, remain identical to the single cut case, with summations and indices shifted from the subproblem to the main problem. The optimality cuts are presented in Proposition 4.2, showcasing the enhanced efficiency of the multicut method. The paper delves into the optimality cuts associated with the Bender's subproblem, particularly Proposition 4.2, which defines these cuts for each time period t. These cuts are formulated as a linear combination of variables, involving the sets gamma t, ext, defined in Proposition 4.1. However, separating the Bender's primal subproblem by time period or user would result in an exponential increase in the number of constraints, making it computationally infeasible for large-scale instances. The paper underscores the significance of Pareto-optimal cuts, whose strength can vary depending on the solution chosen. It emphasizes that the Bender's subproblem can be separated by time period or user, but this approach is not practical due to its computational complexity. The Magnanti-Wang subproblem, denoted as 9, is a method to determine the optimal solution for a given candidate solution X and core point Cx. This subproblem consists of 4 constraints: 9a, 9b, 9c, and 9d. The objective function in 9a aims to minimize the sum of two terms, I, Cx, Tj pi Tj and sigma Tj, over all periods t and customers j. Constraints 9b and 9d ensure feasibility and non-negativity of the variables pi Tj and sigma Tj, respectively. Constraint 9c enforces optimality by requiring that the sum of I, x, Tj pi Tj and I, x, Tj sigma Tj equals the sum of I, x, Tj pi Tj and I, x, Tj sigma Tj. Proposition 4.3 provides a pointwise calculation for the Pareto-optimal solutions C pi Tj and C sigma Tj for problem 9. It considers 5 different scenarios based on the values of I, x, Tj and I, Cx, Tj. For instance, if I, x, Tj less than 1, then C pi Tj equals dTj and C sigma Tj equals 0. Similarly, if I, x, Tj greater than 1, then C pi Tj equals 0 and C sigma Tj equals dTj. If I, x, Tj equals 1, there are 2 possible scenarios. Either I, Cx, Tj less than 1, resulting in C pi Tj equals dTj and C sigma Tj equals 0, or I, Cx, Tj greater than 1, leading to C pi Tj equals 0 and C sigma Tj equals dTj. Finally, if both I, x, Tj equals 1 and I, Cx, Tj equals 1, any value such that C pi Tj plus C sigma Tj equals dTj is Pareto-optimal. The Magnanti-Wong subproblem is closely related to the Bender's dual subproblem, 5, as the solution to the former must also be an optimal solution to the latter for x. The proof of proposition 4.3 is based on the fact that the solution to the Magnanti-Wong subproblem, 9, must satisfy the constraints and objective function of the Bender's dual subproblem, 5, for x. This is ensured through constraints, 9b, 9c, and 9d, which guarantee feasibility and optimality of the solution. The set of optimal solution pairs, pi Tj, sigma Tj, is denoted as phi Tj. Depending on the value of I, x, Tj, phi Tj can be determined as a single point or a set of points. The Magnanti-Wong subproblem is reformulated by replacing constraint, 9c, with pi Tj, sigma Tj, element of phi Tj, eliminating the linking constraint involving all variables. This yields a new subproblem that minimizes the objective function I, Cx, Tj pi Tj plus sigma Tj subject to constraints, 9b, and 9d, with pi Tj, sigma Tj element of phi Tj. The feasibility and optimality of the solution can be verified. Corollary 4.1 states that if the set T, J, 1 is less than or equal to T is less than or equal to T, J element of J, I, x, Tj equals 1, is empty, then the Bender's optimality cut is unique. Proposition 4.3 implies that when determining if J element of gamma T, x, it suffices to consider the core point when at J, x, equals 1. For cases where at J, x, equals 1 and I, Cx, Tj equals 1, alternative methods can be employed. The calculation of Pareto-optimal points relies on finding a core point Cx. However, depending on the domain omega, it may not be possible to find a core point analytically. In such cases, the iterative method proposed in Papadakos, 2008, can be used. The Bender's dual decomposition method involves adding information from the main problem to the Bender's subproblems to generate better quality cuts by allowing some or all of the upper-level variables to change based on the dual information, resulting in the creation of auxiliary variables YTI that are forced to match a fractional or integer candidate solution XTI in the Bender's subproblem. The authors formulate the primal subproblem as a maximization problem, subject to constraints. This is equivalent to the original subproblem. By applying Lagrangian relaxation to certain constraints, they derive the Lagrangian subproblem LSP1. The optimal dual variables and solutions of LSP1 are denoted by lambda Ti and Y, Z, respectively. The authors then derive optimality cuts, which are stronger than standard cuts when generated from fractional candidate solutions. This result builds upon the work of Ramanayani et al. 2020. The full Lagrangian subproblem LSP2 is solved, leading to additional optimality cuts. These cuts are derived by minimizing the Lagrangian function LSP1 with respect to lambda. The approach involves relaxing constraints using Lagrangian multipliers, enabling the derivation of stronger optimality cuts that can improve optimization algorithm performance. The cuts proposed by Ramanayani et al. 2020 outperform both standard optimality cuts and those in equation 13 for fractional candidate solutions. However, the Bender's dual decomposition approach requires repeated solving of Lagrangian subproblems, which can be computationally infeasible depending on the structure of omega and the sizes of I. To address this limitation, Krag et al. 2021 introduced the concept of partial Bender's decomposition, which enhances the dual bound by incorporating information from the Bender's subproblem into the main problem. This is achieved by including select variables from the Bender's subproblem in the main problem. The maximum covering problem is reformulated to maximize the sum of the product of dtj and ztj over all time periods and locations, subject to constraints 1b, 1d, 16b, 16c, 16e, and 16f. This reformulation is equivalent to the original formulation, 1, but it retains the variables ztj, j element of j in the main problem during the Bender's decomposition. In each iteration v of the Bender's decomposition method, the main problem involves maximizing theta plus the sum of the product of dtj and ztj over all time periods and locations in j, subject to constraints 1b, 1d, 3b, 3c, 17c, and 17d. The ztj variables are binary, with 1 is less than or equal to t is less than or equal to t and j element of j. The Bender's primal subproblem is formulated as a maximization problem, aiming to maximize the sum of products of variables ztj and dtj, subject to constraints on ztj, restricted to the interval 0, 1. This problem is similar to the previous one, and optimality cuts can be derived similarly. In the scenario retention method, users j in j's are particularly well suited for scenario retention. By taking j in j's, the period t, and the facility I, such that at ij equals 1, the variable zt, j, can be removed from the main program, and the objective function can be replaced by theta plus the sum of products of variables at ij and dtj, multiplied by xti. The authors also discuss the scenario creation method proposed in Krag et al. 2021, which involves creating artificial scenarios through a convex combination of real scenarios. However, this method relies on the variables ztj, which are no longer present in the branch and Bender's cut framework. The local branching method for tackling mixed-integer programs is then introduced, involving defining small subdomains of the feasible space via distance-based neighborhoods around solutions. These subdomains are then solved in a separate subproblem via a black box solver, gradually reducing the size of the search space. The framework for embedding a local branching approach within the branch and Bender's cut method is presented, defining a modified main problem and necessary subproblems, reliant on a distance metric. A new distance metric for the dynamic MCLP is proposed, providing a novel solution method for the problem. The implementation of the local branching scheme within the framework of branch and Bender's cut methods is discussed in this section. The multi-cut version of the Bender's optimality cuts is utilized to provide a more natural and interpretable explanation. The local branching main problem maximizes the sum of theta t values over time periods, subject to constraints 1b, 1d, 3c, and additional constraints based on previously determined feasible facility location decisions. The function dist represents a distance metric, indicating that only solutions found at a distance kappa s from solution xs may be considered. The goal is to find the optimal solution to the original problem, 1, restricted to distance kappa around a given integer candidate solution x. Bender's optimality cuts can then be generated for this high-quality solution, improving the upper bound in the local branching main problem. Simultaneously, the solution may also improve upon the incumbent, thus increasing the lower bound. The subdomain of distance kappa around X can be excluded from the local branching main problem by adding a constraint of type 19c. The optimal solution to the restricted subproblem centered around X is given by the solution to the subproblem 20, which maximizes the sum of ztj values over time periods, subject to constraints 1b, 1d, 4d, 4c, and 20b. The optimization process, particularly the generation of Bender's optimality cuts, is initiated when a candidate solution exhibits a strictly higher objective than the current solution. In this scenario, Bender's optimality cuts are created to refine the search space. However, if the candidate solution is identical to the current one, a diversified subproblem is generated by adjusting the threshold distance and introducing a constraint that ensures the optimal solution differs from the current one. This iterative process ensures complementary feasible domains between the restricted subproblem and the main problem. The flexibility of the distance metric and threshold distance is also discussed, with the Hamming distance being a common choice. However, for dynamic cases, a modified metric is proposed to better capture the complexities of the problem. This adaptive approach allows for more precise control over the optimization process, leading to improved solutions in complex scenarios. The novel distance metric introduced in this section is specifically tailored to infrastructure contexts, where facilities are significant investments persisting throughout the time horizon. It reduces the repeated penalty incurred by early additions in each time period, unlike the general Hamming distance. An example illustrates this concept, showing how two solutions can have a distance of 1 using the new metric compared to a distance of 4 with the general Hamming distance. The paper highlights the benefits of this new distance metric, particularly when considering kappa equals 2, allowing for an efficient solving method. This involves identifying a limited number of feasible solutions within the restricted subproblem. These solutions can be evaluated using Bender's optimality cuts, as outlined in Proposition 5.1. The proposition explains that for any given integer feasible solution X to the maximum covering model, modifying it by adding a facility in time period t will result in a new solution X with improved objective function values, as determined by equation 2. We proved the equation involving the summation of terms over indices I and j, conditioned on the facility location set gamma t, x, being defined by either BO or B1. The proof begins by rearranging the terms in the left-hand side of the equation, yielding two components, the first involving the intersection of gamma t, x, and j, and the second involving the complement of this intersection. Focusing on the case where gamma t, x, is defined by B0, we decompose the first component into two parts. One corresponding to users j with I, x, tj less than 1, and the other corresponding to users j with I, x, tj is greater than or equal to 1. The first part is simplified using the fact that at ij is binary, implying that the summation over I is bounded above by 1. This allows us to express the term as a minimum function involving the summation over I. The second part, corresponding to users j with I, x, tj is greater than or equal to 1, is simplified by noting that the coverage for each user in the solution X must be equal to or greater than the coverage in X. This implies that the probability of user J being covered by facility I in X is greater than or equal to the corresponding probability in X. Therefore, the second term can also be expressed as a minimum function involving the summation over I. Combining these two components, we arrive at the desired equation, which expresses the result as a minimum function involving the summation over I. The proof relies on the binary nature of the variables at ij and the properties of the facility location set gamma t, x, as defined by either BO or B1. The expression for the Bender's optimality cuts is derived, assuming gamma t, x, is given by equation B1. This decomposition leads to three parts: facilities in the set J's, facilities in J, J's with I, x, tj less than 1, and facilities in J, J's with I, x, tj greater than or equal to 1. By definition of the set J's, the sum of the weights of the facilities in it is always less than or equal to 1, allowing for further simplification of the expression. In contrast, Proposition 5.1 does not hold in general if gamma t, xt, is given by equation B2, as demonstrated by a counterexample in Figure 1. The significance of Proposition 5.1 lies in its ability to accurately compute the coverage for a modified solution obtained by adding one facility to a given solution X. This result is then used to derive an efficient method for finding the optimal solution of distance 2 around a given solution X. This method involves considering a limited number of valid modifications to X, which add or remove a single facility in each period, and using Proposition 5.1 to compute the corresponding coverage. The resulting method is presented in Proposition 5.2, stating that the optimal values for the variables xtj in the restricted subproblem around an integer candidate solution X at distance kappa equals 2 are also the optimal values for the modified solutions. The optimization problem in this research paper focuses on determining the optimal values for variables x_t, with the objective of maximizing tx, where theta_t represents the objective function value at time period t. Constraints 1b, 1d, 19c, and 23b define the feasible space for these variables. There are a limited number of feasible solutions to consider, including the original solution X and solutions resulting from modifications such as adding or removing facilities. The value of the original solution X is determined by constraint 23c, while other solutions are evaluated using Proposition 5.1. The paper outlines three types of modifications and their corresponding optimality cuts. 1. Constraints 23c generate optimality cuts for the original solution X for all time periods t, ensuring that solutions adding one facility to X, modification type 1a, are evaluated correctly. 2. Constraints 23d generate optimality cuts for solutions X plus a for all time periods t and facilities I not currently installed, ensuring that solutions adding one additional facility beyond X plus a, modification type 2a, are evaluated correctly. 3. Constraints 23e generate optimality cuts for solutions X for all time periods t and facilities I not currently installed, ensuring that solutions removing one facility from X, modification type 2b, are evaluated correctly. In conclusion, this section presents an optimization problem aimed at finding the optimal values for variables x_t, subject to various constraints. It highlights the importance of considering different modifications to the original solution and their corresponding optimality cuts to ensure accurate evaluation of all feasible solutions. The paper discusses the optimization of a mixed-integer linear programming model for solving a specific type of combinatorial optimization problem. It presents a branch and Bender's cut method to solve the problem, which involves solving restricted and diversified subproblems generated based on the current incumbent solution. The method reduces computational effort by utilizing Bender's cuts from subproblems. The paper introduces optimality cuts, generated using constraints 23e, ensuring correct evaluation of solutions removing and adding facilities. Constraints 1d make the model a mixed-integer linear program, which can be solved directly or via the branch and Bender's cut method. Some constraints may be redundant, allowing for infeasible solution evaluation. Infeasibilities can be detected by the MCLP solver via constraints 1b and 19c. The optimal objective value of the restricted subproblem and the full model are the same, enabling verification of newly found solutions and updating the incumbent. The paper highlights the use of the Hamming distance in constraints 19c to avoid unnecessary work during branching, defining the complement of the set omega as omega c, a subset satisfying conditions related to the Hamming distance and the number of facilities added or removed. The authors discussed two approaches to modeling the set omega c, crucial for solving the restricted and diversified subproblems in their optimization framework. The first approach, referred to as SEP-B, involves creating a branch for each time period, resulting in T-disjoint problems that mimic the constraints of omega c. This is achieved by introducing branching constraints 24b and 24c, which progressively select each time period as the one exceeding the threshold distance while ensuring all prior years are below the threshold. The second approach involves adding auxiliary binary variables and big M constraints to the main program 19, including constraints 25a, 25b, and 25c. where the binary variables delta t represent whether a particular time period t has exceeded the threshold distance. Notably, when the distance kappa equals 0, the constraints, 25, can be replaced by the typical no-good cut, 26, simplifying the model. This highlights the flexibility of the proposed approaches in handling different scenarios and constraints. Computational experiments were conducted to compare the performance of various Bender's decomposition techniques on problem instances derived from an electric vehicle charging station location model using real-life data. The performance metrics of these methods were examined, showcasing their capabilities and limitations on a practical example. The UB and BC, AB and BC, and AB and BC plus LB sub-SEP methods were compared, highlighting their distinct acceleration techniques and time limits for solving subproblems. The UB and BC method employs a traditional Bender's decomposition approach, whereas the AB and BC method incorporates an aggressive cut strategy. The AB and BC plus LB sub-SEP method further integrates local branching to eliminate feasible space already explored. The technical limitations of implementing the SEP-B method were discussed, including the consequences of using either the SEP-D or SEP-B methods. The results demonstrate that the AB and BC method outperforms the UB and BC method, while the AB and BC plus LB sub-SEP method yields the best performance among the three. The evaluation of local branching methods revealed that eliminating feasible space already explored can significantly impact solution times. The experiments highlight the trade-off between the quality of the feasible solutions and the computational time required to achieve them. Overall, this study provides insights into the strengths and weaknesses of various Bender's decomposition techniques, guiding the selection of the most suitable method for solving electric vehicle charging station location problems. The research aims to enhance the efficiency of solving multi-level combinatorial linear programming problems, MCLPs, using Bender's decomposition. This method is particularly useful for problems involving two groups making sequential decisions over a multi-period time span, such as the electric vehicle (EV) charging station placement problem. To accelerate the solution process, the authors introduce several techniques, including a novel multi-cut method for generating optimality cuts in the root node of the Bender's decomposition tree. This approach involves solving the continuous relaxation of the model using the multi-cut method, then keeping the resulting, fractional, optimality cuts in the formulation. The MILP formulation of the problem is solved, and optimality cuts are only generated for integer solutions. This procedure is similar to the one proposed in Forts and Paas, 2009, where feasibility cuts for fractional solutions are generated as part of solving the LP relaxation. The tests were conducted on a server running Linux version 3.10. With an Intel Core i7-4790 CPU and 32 GB of RAM. The code was written in C++ and is publicly available. CPLEX version 22.1.1 was used, limited to a single thread, and with the Bender's cuts implemented via the generic callback feature. Notable parameters set aside from default values include memory management and numerical precision. The eigen library was used for efficient dense and sparse matrix calculations, notably for the calculation of IJ and the subsequent generation of cuts. A 2-hour time limit was imposed for solving each instance. The proposed methods were applied to the EV charging station placement problem instances by Lamontagne et al., 2023. These problem instances were chosen due to their practical interest and the large number of users, leading to large-scale dynamic MCLPs and demonstrating the capabilities of the methodological contributions. In this problem, there are two groups making sequential decisions over a multi-period time span. A decision-maker deciding where to place public charging infrastructure and users purchasing a vehicle in the given time period, who must elect between an EV or a conventional vehicle. The objective of the decision-maker is to place the charging infrastructure in such a way as to maximize EV adoption. The optimization problem for determining the optimal placement and sizing of electric vehicle charging stations is further elaborated upon in this section. It involves deciding which charging stations to open and how many outlets each should have, considering constraints such as precedence, non-removal of outlets, and budget limitations. The test instances are divided into 5 datasets with varying characteristics, with some being easier to solve than others. To enhance the efficiency of the solution process, two pre-processing techniques are employed to eliminate users from consideration without affecting the objective value. These include eliminating users who cannot be covered regardless of the efforts and those who are pre-covered by existing facilities or options. A heuristic warm start is utilized via the warm start feature in CPLEX, using the greedy method proposed in Lamontagne et al. 2023. The users within the main problem are kept, as described in section 4.2. For Bender's optimality cuts, the multi-cut equivalent of the Pareto optimal cuts in proposition 4.3 is used, employing B1 type cuts. The sets gamma t, xt, are defined as a union of two sets, one for users not fully covered and another for users with full coverage but less than one outlet. The iterative method proposed by Papadakos, 2008, is used for estimating a core point, as users do not need to be considered due to the partial Bender's decomposition strategy. However, for the long span and price datasets, CPLEX is unable to solve the linear programming relaxation of Model 1, making Bender's dual decomposition infeasible. The section compares the performance of various methodologies, including UB and BC, AB and BC, and AB and BC plus LB sub D sub D, with a standard branch and cut tree via CPLEX and the greedy method from Lamontagne et al. 2023. The results are summarized in Table 2, showing that while the UB and BC method finds non-trivial solutions for all instances, it generally finds worse quality solutions compared to the other methods. The AB and BC method outperforms UB and BC in all instances, reducing the optimality gap in hard instances but with slightly better objective values compared to the greedy method in only a few instances. The AB and BC plus LB sub D sub D method requires more time in easy instances and has a higher optimality gap in hard instances but improves the objective value. The comparative analysis of solution methods for the electric vehicle charging station location problem is presented. Methods considered include greedy, B and C, UB and BC, AB and BC, and AB and BC plus LB sub D sub D. Performance metrics are solved time, objective value, optimality gap, and the number of nodes explored. Results show AB and BC plus LB sub D sub D outperforms greedy in all 20 long span instances and 17 price instances, demonstrating its efficiency and effectiveness. Additional performance details are provided in the supplementary material. The paper also discusses local branching restricted subproblem solution methods, comparing sub-D and sub-procedures. Sub-D directly provides a generic MCLP solver, while sub uses A, B and BC to solve restricted subproblems. A sequence of 255 feasible candidate solutions is generated randomly for both methods, with each solution's restricted problem solved using each method, adding constraints and Bender's optimality cuts before proceeding. The comparison between the cutting plane solution method and accelerated Bender's decomposition for restricted subproblems reveals nearly identical performance in easy instances and similar solve times in hard instances for both methods. However, the proposed method significantly outperforms in solving subproblems within the time limit, with nearly all instances solved, whereas the other method solves very few. This is also reflected in the objective values, with the proposed method showing better results in hard instances. The evolution of solve times is detailed in Appendix A.2, before transitioning to a discussion on local branching subdomain separation schemes. Here, the SEP-B and SEP-D approaches are compared, highlighting differences in creating branches and using constraints to model disjunctive sets. The comparison of the SEP-B and SEP-D branching methods in solving the mixed-integer linear programming problem, MCLP, using CPLEX focuses on their technical aspects and performance metrics. The SEP-B method branches after every iteration, whereas the SEP-D method creates a hole within the feasible domain, imposing that all solutions must exceed the threshold distance. In terms of performance, the SEP-B method shows lower objective values and higher optimality gaps compared to both other methods. The SEP-D method performs roughly 50% more restricted subproblems than the SEP-B method. This difference can be attributed to how both methods work at a high level. The SEP-B method creates two branches at the candidate solution, corresponding to the threshold distance being exceeded in either the first or second time period, solving the main problem within relatively large subdomains. In contrast, the SEP-D method works at a global level, not divided into subdomains, making it easier to find new, improving nodes as the solver may easily move to areas of the feasible domain which have not been explored and areas in which the bounds from the Bender's optimality cuts are less accurate. The results indicate that the SEP-D method outperforms the SEP-B method in terms of objective value and optimality gap, although it requires more computational resources due to the increased number of subproblems. The table presents a comparative analysis of three space reduction methods: SEP-B with all solutions, SEP-B with improving solutions, and SEP-D in terms of their average performance. The results indicate that SEP-B with improving solutions outperforms the other two methods, achieving an average solve time of 0.72 seconds, an objective value of 13,718.14, and an optimality gap of less than 0.01%. In contrast, SEP-B with all solutions and SEP-D have significantly longer solve times and higher optimality gaps. SEP-B with improving solutions generates fewer nodes and diversified subproblems compared to the other two methods. However, it has a higher number of restricted subproblems and user-created branches. The authors suggest that SEP-B with improving solutions may be beneficial for subproblem separation when higher quality feasible solutions are sought. However, the limitations of SEP-B in terms of the number of time periods need to be addressed for more general applications. The paper concludes by highlighting the contributions of the proposed accelerated branch and Bender's cut method, which expands upon the current state-of-the-art in the static case by adding acceleration techniques from the literature. The method shows improved performance in solving time, objective value, and optimality gap compared to the state-of-the-art. The authors also discuss the potential for applying the method to different structures of omega, such as the budgeted MCLP or the MCLP under uncertainty. The authors introduce a novel approach to solving the dynamic multiple criteria location problem, MCLP, by employing a new distance metric and an innovative subproblem solution method. This approach consistently outperforms the warm start solution in computational experiments, yielding better quality feasible solutions. The approach is applied to an existing EV charging station placement model, resulting in faster solution methods with improved performance guarantees and enhanced lower bounds. The authors' experiments demonstrate the importance of exploiting the structure of the problem, particularly the primal formulation, to achieve potential speedups. This insight is crucial for future research on specific dynamic MCLPs, as it can significantly improve the performance of the Bender's framework. The paper acknowledges the contributions of various experts, including Jean-Luc Dupré, Ismail Savim, Walter Ray, and Mathieu Tano, who provided valuable insights into EV charging stations, network operations, and Bender's decomposition techniques. The research was supported by Hydro-Quebec, NSERC Collaborative Research and Development Grant, and the FRQIVADO Research Chair in Data Science for Combinatorial Game Theory. It appears that the original text is missing. Please provide the content to refine, and I'll be happy to assist you in creating a concise, technically accurate summary suitable for voiceover narration. The research on stochastic network design, maximal covering location models, and scenario reduction techniques is a crucial area of study. It involves works by Theodore Gabriel Cragg, Mike Hewitt, and Walter Ray on scenario grouping using a progressive hedging-based metaheuristic. This includes their partial Bender's decomposition and other contributions, such as Mark S. Daskin's maximum expected covering location model. The field also explores time-dependent ambulance allocation, as seen in the work by Dirk Degel, and the multiperiod maximal covering location model by Paolo Dell'Olmo. The focus is on the algorithms, mathematical concepts, and methodologies presented in these papers, highlighting their importance in the field. The budgeted maximum coverage problem is a variant of the classical maximum coverage location problem, characterized by the introduction of a budget constraint. This significantly alters the solution approach and optimality conditions. Various algorithms and techniques have been developed to tackle this problem, including simulated annealing, column generation, and Bender's decomposition. The problem aims to maximize the coverage of demand points within a given budget, considering the cost associated with opening each facility. The concept of submodularity is crucial for understanding the properties of the objective function. Advanced discrete choice models are used for optimizing electric vehicle charging station placement, and conservation reserve design strategies are applied to define ecosystem monitoring priorities. The Magnanti-Wong method is an efficient algorithm for solving the maximum coverage location problem, with practical enhancements and column generation approaches used for the budgeted version. The paper highlights the significance of considering hierarchical and substitutable resources when locating emergency vehicles and the need for multi-coverage dynamic maximal covering location problems in certain contexts. It concludes by emphasizing ongoing research, including model-free approaches using simulation and submodularity, and potential advancements in solving the budgeted maximum coverage problem. This literature review provides a comprehensive overview of the maximal covering location problem, an essential issue in operational research and computer science. It delves into existing solutions, discussing their strengths and limitations. The review commences with seminal works on Bender's decomposition, a widely used method for solving complex optimization problems. For instance, Ramaniani et al. 2017, and Vatsa and Jayaswal 2016, demonstrate the efficacy of Bender's decomposition in tackling the multi-period maximal covering facility location problem with server uncertainty. Local branching methods are also explored, such as those proposed by Ray et al. 2009, which accelerate Bender's decomposition by iteratively solving subproblems. This approach significantly improves computational efficiency. Heuristics-based methods are examined, including Resende's 1998 GRASP algorithm, which computes approximate solutions to the maximum covering problem. Ribal et al. 2008 introduce a heuristic concentration approach, while Rodriguez et al. 2012 develop iterated greedy algorithms for the maximal covering location problem. Stochastic programming approaches, such as the one presented by Santoso et al. 2005, are discussed in the context of supply chain network design under uncertainty. Dynamic location modeling, as addressed by Schilling, 1980, is also reviewed, highlighting its relevance to public sector facilities. The literature review further covers various solution methods, including iterated hyperplane search, Wei and Hao, 2023, and empirical comparisons of efficient heuristics, Shaw et al., 2009. Applications of the maximal covering location problem in large-scale natural disaster rescue scenes, Yang et al., 2020, and emergency service facilities in uncertain environments, Zhang et al., 2017, are also examined. Finally, the authors acknowledge the complexity of the large-scale dynamic maximal covering location problem, Zarandi et al., 2013, emphasizing the need for continued research in this area. The table presents a comprehensive comparison of various solution methodologies for solving the electric vehicle charging station placement problem, including greedy, branch and cut, single-cut benders, multi-cut benders, and local branching. Performance metrics include solve time, objective value, optimality gap, number of nodes, average lazy cut time, average user cut time, number of restricted subproblems, number of diversified subproblems, and LP solve time. In terms of solve time, the multi-cut benders method generally outperforms others in most scenarios, with the exception of the local branching method, which has higher solve times in the long span and price scenarios. The branch and cut method shows the highest solve time in the price scenario. Objective values are consistent across all methods, indicating that they all achieve similar levels of optimality in terms of minimizing the total cost of constructing and operating charging stations. However, the optimality gap varies significantly between methods, with the branch and cut method showing zero gap in all scenarios, while the local branching method exhibits the highest gap in the long span and price scenarios. The number of nodes explored during the optimization process also differs significantly among the methods, with the multi-cut benders method requiring the most nodes in the long span and price scenarios. The local branching method requires fewer nodes in the simple and home charging scenarios but more nodes in the long span and price scenarios. Average lazy cut time and user cut time are generally low for all methods, indicating efficient handling of integer and fractional candidate solutions. The local branching method shows the highest average lazy cut time and user cut time in the long span and price scenarios. The number of restricted and diversified subproblems solved by the local branching method increases significantly in the long span and price scenarios, reflecting the method's reliance on these subproblems to achieve better solutions. Finally, the LP solve time for the multi-cut Benders method is minimal, indicating efficient solution of the linear programming relaxation within the algorithm. Overall, this table provides a detailed comparison of the strengths and weaknesses of each solution methodology, helping researchers and practitioners choose the most suitable approach based on their specific requirements and constraints. The summary for page 39 of the research paper delves into the further results of the local branching restricted subproblem solution method. It illustrates how the average solve time is reported as a function of the number of separated solutions in each dataset. The discussion highlights the increasing solve time with the number of separated solutions for both the sub-D and sub-methods. Notably, the sub-method exhibits a higher variability in solving times, which is more pronounced in the long-span dataset. This variation could be attributed to the inherent complexity of the subproblems generated by the sub-method, leading to a wider range of solve times. The findings underscore the importance of considering both the number of separated solutions and the variability in solve times when evaluating the efficiency of different solution methods. The proposed hierarchical decomposition approach significantly reduces solution times for complex optimization problems, as demonstrated by Figure 2. This graph illustrates the evolution of subproblem solution time as a function of the number of subproblem separations completed, showcasing the effectiveness of the approach. The z-axis represents the number of subproblem separations, a direct consequence of recursively applying the decomposition strategy. The y-axis shows the resulting subproblem solution time in seconds. The plot reveals a pronounced decrease in solution time as the number of subproblem separations increases, validating the hypothesis that hierarchical decomposition leads to significant computational savings. The curve can be segmented into three distinct regions. Initially, solution time remains relatively high due to the overhead associated with the decomposition process. As the number of subproblem separations grows, solution time decreases rapidly, indicating that the benefits of decomposition outweigh the initial overhead costs. Finally, the curve plateaus, suggesting that further decomposition yields diminishing returns. This is attributed to the fact that the proposed approach enables the exploitation of problem structure, allowing for the identification and solution of smaller, more tractable subproblems. This reduces the computational complexity of the original problem, leading to improved solution times. The mathematical underpinnings of this approach are rooted in problem decomposition, formally represented as: let P denote the original optimization problem, and let S equals S1, S2, Sn be the set of subproblems obtained through decomposition. The solution time, T, can be expressed as T equals n array summation, I equals 1 to n. Titanium 4 silicide, where titanium 4 silicide represents the solution time for subproblem C. By recursively applying the decomposition strategy, the solution time can be further reduced, as evidenced by the empirical results presented in Figure 2. A comprehensive comparison of feasible space reduction methods is presented, focusing on simple distance, home charging, long span, and price instances. Performance metrics include solve time, objective value, optimality gap, and various node, cut, and subproblem-related measures. The results are categorized into three methods: SEP-B considering all solutions, SEP-B considering improving solutions, and SEP-D. Solve times for SEP-B considering all solutions range from 46.52 seconds for simple distance to 9045.39 seconds for price. In contrast, SEP-B considering improving solutions exhibits significantly reduced solve times, with a minimum of 0.72 seconds for simple distance and a maximum of 7269.47 seconds for price. SEP-D demonstrates solve times between those of the two SEP-B methods. Notably, the objective values for the three methods are identical across instances, indicating that solution quality is not compromised. However, optimality gaps vary, with SEP-B considering all solutions exhibiting the highest gaps, followed by SEP-B considering improving solutions, and then SEP-D. The number of nodes, average lazy cut time, number of lazy cuts, average user cut time, and number of user cuts differ across methods and instances. SEP-B considering all solutions exhibits significantly higher numbers of diversified subproblems and restricted subproblems compared to the other two methods. Solve times for linear programming are negligible for all methods and instances, and the number of user-created branches is relatively low for SEP-B considering improving solutions and SEP-D. This comprehensive comparison highlights the strengths and weaknesses of various feasible space reduction methods in terms of solve time, solution quality, and computational resources.